So I guess we should start for the last session, which is the Numerical and AI tool to enhance FOWT design and operation. It's a very diverse session where we will see different applications of numerical codes, AI algorithm to solve different problems in the offshore wind and floating offshore wind industry. And we will start by a talk by Alexis Mérigot from IFP Energy Nouvelle. He will talk about application of real-time wave forecasting in floating offshore wind. And Alexis is a researcher at IFPEN with an extensive expertise in wave energy that is now transferring his skills in terms of wave modeling, wave predictions to floating offshore wind with application to control of the turbine and also crew transfer for operation and maintenance. And this would be basically the topic of the discussion he will give us today.
Okay, anyway, hi everybody, and thank you Jean-François for the accurate introduction. My talk today is about forecasting waves in real time and how this may be useful in the offshore wind context. So first I'm going to introduce you what we mean by forecasting waves in real time and highlight possible applications in floating wind. And then I will try to give you an overview of the state of research in the area, with obviously a focus on our own contributions. So I like to define real-time wave forecasting as predicting wave-induced motions or forces on a second-by-second basis with prediction horizons between a few seconds and several minutes, and also based on local measurements that are updated in real time. So that's quite different from the more better-known sea-state forecasting or met-ocean forecasting, where timescales are typically about an hour at least, and only statistically averaged quantities are typically predicted. So we see two main types of applications for real-time forecasting that Jean-François briefly highlighted. The first one is predictive control, and the second one is decision support and early warning. So let's now see how these can apply in the floating wind context. So first, predictive control. The pitch angle control of a floating wind turbine could, in principle, benefit from real-time wave predictions, with two possible objectives that are a reduction in wave-induced loads and motions, or a reduction in wave-induced power fluctuations. So here I encourage you to have a look at the very interesting FOWT project that investigated those two objectives. And one of the main findings was that decreasing wave-induced motion was almost impossible and came at huge costs in terms of blade pitch actuation, while reducing wave-induced power fluctuation was achievable using rather reasonable pitch actuation. Now, regarding decision support and early warning, well, if you can forecast waves in real time, then you can anticipate dangerous motions that can occur during offshore operations, especially crew transfer, but that's not the only case. And so by predicting those dangerous events, you are making the operation safer. And by doing so, you can allow this operation to take place in slightly larger sea states. By doing so, you improve wind turbine accessibility. And by doing so, you decrease downtime and eventually increase annual energy production. So this is true, obviously, for fixed wind turbines, but it's even more true, I would say, for floating wind, and that's mainly due to the more exposed and distant locations that are typically chosen. So now, where is research in this domain at the moment? So any method to forecast waves will rely on live sensing of the wave field. But then this has to be fed in a numerical model, and so all methods will differ depending on the numerical models that they use. In the large majority of cases, the model is deterministic and physics-based, so it assumes that the wave field can be decomposed in a finite number of wave components, and the amplitudes and phases of these wave components are identified from measurements. And then they are propagated in space and time using numerical models, physical numerical models. Now, if you allow the number of such wave components to grow to infinity, then you end up with the very well-known and classical Gaussian stochastic description of the sea state. And this happens to also provide a very elegant framework to address real-time wave forecasting. And so this is the avenue that we have taken at IFPEN and that I'm going to describe in a little more detail. Then finally, you have a growing number of purely data-based methods that are typically trained using wave basin or numerically generated wave data. Now, sorry, there are a couple of equations on this slide, but I promise it should be the only one. So how do we implement wave forecasting in our Gaussian stochastic sea state? We want to predict the waves at a nearby location here that you can see it in green over the future next couple of instants using observations that are made at other locations, the distant ones in this example. And so if we take predicted and observed wave elevation values and we stack them into vectors x and y, then with the Gaussian sea state theory, we know that this vector has a Gaussian law. And what's the most important is that we can actually calculate its covariance structure using the wave spectrum. And so using this covariance structure, we have all the information that is needed to achieve optimal forecasts of our nearby wave elevation using the distant wave elevation. And in addition to having the optimal forecast, we also have the uncertainty associated with this forecast. This approach has a number of practical benefits. So I listed the three most important ones here. So first of all, computational time. The only operation to carry out in real time is a linear operation, so it's very fast. In principle, it's optimal, which means that it should perform better than any other approach that uses the same set of measurements. And finally, the prediction uncertainty is provided together with the prediction itself, which I think is quite valuable for an operator. We have now validated this approach in a number of both simulated and real data scenarios. I think the most representative one is the one that you can see playing here, yes. So in this example, that's an actual wave record, recorded by means of a pair of cameras working in stereo. And we are using the blue dot locations to infer the future waves at the red dot locations. And as you can see in this specific example, we are able to forecast waves rather accurately for about 20 seconds into the future. So it may seem little, it's more or less 3.5 wave periods in this sea state. But this very little is actually governed by the field of view that we have. So one more thing that our stochastic approach can teach us is the essential limitations of wave predictability. So basically where you have to look to achieve prediction at a required time horizon. I would say that this can be summarized in two main points. The first one is that the further up wave you look, the further in time you can predict. Okay, it seems quite logical. And we can be a little more accurate by saying that the rate of this, so the ratio between the time horizon and the distance where you need to look, is governed by the group velocity at the peak wave frequency. So this is illustrated here in these three diagrams. So to achieve an accurate prediction 1 minute in advance. These are the distances where you have to look at the waves depending on the peak wave period. So this tells us that we have to look at least a couple of 100 meters upwave to achieve 1 minute ahead predictions. Then the second main point is that a rather wide field of view, so a wide angular field of view, is required to account for wave directionality. So this is also represented in these three diagrams with three different scenarios in terms of wave directional spreading. So this brings the question of what sensors are available that would allow us to scan the waves under these criteria. And so we came to the conclusion that currently the only remote wave sensors that can achieve, that can allow us to achieve minutes ahead prediction are X-band radars that can scan the wave field over kilometers. But we also realized that inverting radar images to recover the underlying sea surface is not such an easy task, and it's not as well known as we initially thought. So we really see this point as the main current technological bottleneck, because all the fundamental limitations that I showed you in the previous slide, they apply to any method. So we think that eventually all methods should eventually converge to similar performance, but then the true game changer will be to have accurate wave measurements. Okay, now a couple of conclusions. So first, real-time wave forecasting has the potential to lower LCOE in floating offshore wind, even more so than in fixed offshore wind. We can also say that our Gaussian stochastic approach has many practical benefits to achieve real-time wave forecasting. But that being said, we believe that all methods, whether they are data-based or physics-based, they are subject to the very same fundamental limitations. So if they are cleverly implemented, eventually they should converge to similar performance. And finally, we see that accurate and real-time wave sensing using X-band radars is probably the main scientific bottleneck at the moment to achieve accurate minutes ahead predictions. So that's all for me, and I will take any questions during the Q&A session. Thank you.
Thank you, Alexis, and I fully agree that we need either new techniques to analyze data of existing sensor, or we should develop new sensors, maybe as well. Okay, the next speaker will be Mayren Rosionnet Sanchez-Lara, who is a researcher at Tecnalia with over 13 years of experience in offshore renewable energy, and she specializes in the design and analysis of floating structures and brings deep expertise in hydrodynamics, structural engineering, and marine operation. And she will be talking about digital twin design for hive wind floating substructures at Mediterranean sites.
Hello, good afternoon. Thank you for joining us for the grand finale, the last session on the last day of this great conference. I really appreciate you staying with us. Well, my name is Mayren Sanchez, and I work at Tecnalia, which is the largest applied research and technological development center in Spain. And for those who don't know the company, we are good at solving complex problems that require unique solutions. In the framework of the FOWT project, funded by the Basque government and focused on the development of new operation and maintenance technologies for the floating offshore wind sector, we collaborate with CENER, a leading Spanish engineering company, and together we developed a digital twin for 50 megawatt wind turbine installed on the high wind semi-submersible floating foundation for the Mediterranean conditions. To explain this work, I have structured the presentation into 6 blocks. First, I will introduce the background and motivation behind the project. Then, I will explain the main properties of the digital twin and how we selected the key parameters. After that, I will show a comparative evaluation of different artificial intelligence techniques, starting with classic regression models and progressing to advanced deep learning techniques. And finally, I will share the main conclusions and some ideas for the next steps. Well, our goal in this project is to create a digital twin to predict the loads on the multi-line fair leads of a floating offshore wind turbine using machine learning techniques. And why a digital twin? Because it helps us to improve the operational maintenance strategies, speed up the design and testing, and all in a virtual environment. In the design phase, it means fewer the design loops, better accuracy, and faster development using synthetic data. During the operation phase, it allows us to make decisions based on real data and to detect problems before they happen. So in the end, it can be translated into better turbine availability and performance. As we didn't have access to real operational data, we use synthetic data generated with an open-fast model. The output we want to predict is the tension at the 3 fairlead points, which are the connection points between the floater and the mooring lines. The input to the digital twin includes platform motions, displacements, rotations, velocity, and accelerations, and we also include weight height as a key environmental input. To identify the most relevant input variables in the simulation field, we perform a feature analysis using 3 criteria. A correlation between variables, variance, and relevance of the variables in the reference regression model. Based on this analysis, we selected 2 groups of variables to evaluate the performance of the predictive model. The first group includes surge, sway, yaw, and with elevation. And the second group includes swoop, sway, and horizontal acceleration and velocity in surge direction. The first predictive model we use is a random forest, which is basically a method that combines many decision trees to improve the predictions. In this first test, we trained the model without considering time dependence. So a subset of samples was randomly excluded from the training phase, and then used it to evaluate the prediction performance. We measured the accuracy using the mean absolute percentage error, which is basically the percentage difference between the simulated and the real values. And what about the results? Well, we obtained an error close to 0, which means very high accuracy. But this is not a surprise. We expect this because both training and test data came from the same simulation series. So the model is not yet challenged by data variability. In the next step, we introduce time dependence using an iterative prediction model. This means that instead of predicting based on a single isolated point in time, we now use the value at time t together with the previous values like t-1 in order to predict what happens at t+1. So in this case, the training data includes the temporal evolution and not just a snapshot. So in addition, we implemented a prediction window where the model forecasts a sequence of values over a given period, rather than making isolated predictions. And to get the best results, we also resample the data every second and reevaluate the model afterwards. With this setup, we achieve an error below 6%, which is very promising for a train-aware prediction of loads. In the next step, a challenging scenario was analyzed. We trained the model without extreme values, which basically means that we omit high wind speeds. So the linear regression model that previously performed well now show large deviation under these conditions, because regressive models work well for interpolation, but perform poorly for extrapolation. So to solve this, we developed a model combining the nonlinear capabilities of random forest with the simplicity of a linear regressor. In the first approach, training was done completely without extreme wind speeds, and we saw very poor performance, with error values up to 110% in the worst cases. Then we tried a better approach, randomly including some extreme wind speeds in the training data, and this gave much better results for previously unseen scenarios, reducing the worst case error to around 20%. To improve the accuracy of the load predictions compared to the previous models, we developed a new model based on artificial neural networks. A neural network is basically a machine learning model inspired by the human brain, and it's made up of layers of interconnected neurons that can learn complex patterns in the data. So first, we trained the network without including high wind speed cases, and the results showed a considerable improvement over the previous models, with error around 40% in the worst scenarios. Then we trained the network, including high wind speeds and 2 random wind directions. In this case, for the scenarios that were included in training, the model performed almost perfectly. And even for unseen scenarios, the error was below 13%, which is a notable improvement over the previous random forest plus linear regression combination. So as a next step, we propose a lower approach to progressively improve the model, aiming to enhance the accuracy without full retraining of the model. So this approach has been implemented using TensorFlow library. So we explored two different strategies in this case to handle time-varying data more effectively. The first one is a time series approach using long short-term memory network, which is a type of recurrent neural network designed to learn from sequences of data. So, however, we observe a strong sensitivity to sequence order when the model sees data that is out of the expected time sequence. Performance drops significantly, and in some cases, the model becomes unreliable. So to address this, we apply the second strategy. In this case, it's a regression-based approach using a feed-forward neural network combined with transfer learning. Here, only the final layer of the model is retrained, so we need data. So this allows the model to adapt without forgetting what it already learned. This approach shows more stable behavior with a mean error under 80%, and even in the worst cases, the deviation remained within acceptable limits and didn't disturb the prediction. So overall, this strategy proved more robust, and especially when the model is exposed to high variable conditions, making it a promising candidate for operational use. To summarize, we tested several predictive models to estimate marine line loads in floating wind turbine, and we can conclude that the random forest plus linear regression model works well when we have high wind reference data. In contrast, artificial neural networks perform better when no reference data is available for extreme conditions. And regarding thin-hour models, the long short-term memory model, although suitable for sequential data, struggles when the sequence is not preserved, and increasing time step does not help. The feed-forward neural network with transfer learning shows the most stable performance, even with limited training data. And by adjusting hyperparameters like learning rate and early stopping, it becomes a strong candidate for real-time applications. And looking ahead, we aim to test these digital twins with real operational data obtained from a control monitoring systems and installed on edge devices. And we will also explore the new digital twin techniques, especially those suited for fault detections and reliability analysis, because our goal finally is to support data-driven operational maintenance strategies, increasing turbine availability and performance. And that's all from my side. Thank you very much for being here, and if you have any question, I will be happy to answer later. Thank you.
Okay, thank you, Miren, for this very nice benchmark of statistical techniques to learn the loads on marine lines. It also shows that it would be variable to team up with pure data scientists on this topic, and but maybe the future of this. Okay, so the next speaker will be Johan Delman from Kent PLC, and he will be talking on similar approaches, and the talk is about harnessing artificial intelligence for efficient floating offshore wind turbine design. And Johan is an engineer who started his career in the automotive industry before moving towards marine renewable energies 6 years ago, where he got actually a training on this in Brest at ENSTA Bretagne. He has since contributed to the development of ambitious pilot projects such as Eolmer.ScotWind, and today he's bringing his engineering expertise to the largest players in the offshore winds at the Kent Engineering Company. So, Johan, the floor is yours.
Thank you. So good afternoon, everyone. Happy to be here back in Brest for a couple of days. Today, I would like to give you some insights about how we use AI tools in our engineering processes, namely in this case for the design of floating offshore wind turbines. So first, a few words about Kent. So we are a global engineering company. We employ over 11,000 people across the globe. We support projects from their early development phase through engineering, construction, operation, and until their final decommissioning. So As an engineer, enthusiastic about floating offshore wind turbine and AI, I naturally asked every possible AI chatbot out there to design for me the optimal floating wind turbine. And although the results were always very funny and sometimes even hypnotic to look at, they were consistently irrelevant. So why is that? Because we're not necessarily all AI experts in this room, I thought it would be useful to define a few of the keywords. So first of all, AI, or artificial intelligence, refers to the discipline. Machine learning is a subdiscipline of AI. It involves simple algorithms. The models go through a supervised learning phase and are then able to classify existing data. Deep learning is itself a subdiscipline of machine learning. It relies on a network of artificial neurons. It goes through an unsupervised learning phase and is then still able to classify only existing data. Now, generative AI, the one we all know since a couple of years, that one, as far as I understood, relies on an even larger network of artificial neurons. It also has to go through an unsupervised learning phase, but is then able to generate new data. So the obvious problem here, so all of these tools, they have to go through a training phase. All of these models have to be trained. And the obvious problem here is that when it comes to floating offshore wind turbines, there is a lack of data to train those models. So our approach at Kent was to say, well, let's first generate this data. So we use our deterministic modeling capabilities to generate this synthetic data, which we feed to a machine learning algorithm to train a response model, which itself is then fed to a deep learning algorithm to train a neural network. So if we come back to the first stage, the deterministic model, this is where the expertise of naval architects and engineers comes in. To produce this synthetic data, you have to develop numerical or deterministic models. And floating offshore wind is by essence a multidisciplinary object. It involves aerodynamics, structural engineering, hydrodynamics. And all of these fields, for all of these fields, there are countless numbers of numerical models, theoretical frameworks. And they're all characterized by at least two aspects: their accuracy and their computing efficiency. And usually, the more accurate they are, the less efficient they are from a computational point of view. Now we go to the next step, the learning algorithm. Again, not a new field of engineering, countless number of methods and tools here. But we can try to classify them, and usually they are all suited for a specific amount of input variables and output objectives. So if you're dealing with only one objective and one input variable, you would use direct search methods or analytical methods. If you're still dealing with one variable, but multiple objectives, you'd use what we call a scalarization approach, where you're trying to transform your vector of objectives into a scalar objective using, for instance, a weighted average. Now, if you have multiple variables, multiple input variables, and only one objective, you could use typical machine learning methods such as gradient-based methods or evolutionary algorithms to try to find, for instance, the maximum of that surface in the bottom right quadrant. But things become a bit more tricky when you have multiple input variables and multiple objectives, because you're not anymore trying to find one single optimum, you're trying to find a set of optimums. For instance, if you look at this graph on the top right, I have two objectives on the x and y axis, which I'm trying to minimize. So there are several solutions, but the only ones that are optimal, which means in this case that are not dominated by any other solution, are represented with orange dots. And they form a sort of frontier border, which we call the Pareto frontier. So to characterize that frontier, you usually need deep learning methods. All right, so now that we all have a strong theoretical background, let's look at a case study. So for a developer gave us a specific rotor nacelle assembly and asked us, well, what is the optimal floater and tower design for this RNA? So the rotor diameter was fixed, the cell mass was fixed, but all the rest was left open, variable. So for instance, the tower diameter, wall thicknesses, the type of floater, the dimensions of the floater, its draft, all of that was considered as an input variable. So you can imagine we had well over 20 variable design parameters. Now, if we look at the output objectives, at first glance, you would think, well, there's only one objective, right? You're just trying to minimize the combined mass of the hull and the tower. Well, indeed, but if you look a bit closer, we also had a lot of constraints. For instance, we want to make sure that the tower can be constructed, so we had to keep the ratio of the tower diameter divided by the wall thickness in a certain range. We also wanted to make sure that the tower would not buckle under extreme loads. And more importantly, we had to make sure that the tower eigenfrequency, so its natural frequency, would not get too close to the blade passing frequency, the one we call 3p. If your tower has an eigenfrequency below 3p, we call it a soft, stiff tower. If it's above, we call it a stiff, stiff tower. Now, usually you want to have a soft, stiff tower because soft towers are flexible and therefore lighter and cheaper. All right. Sorry. So in optimization problems, constraints and objectives are more or less the same. So we had, again, maybe only one objective, but well over 30 constraints. So we developed the deterministic numerical models for this study. And with our AI tool, we were able to assess over 1,000 designs per hour on a classic laptop, your daily work machine. So very quickly, we were able to tell the client, well, look, for this specific RNA, we can't design any soft, stiff tower, no matter the floater you choose, no matter the dimensions. It will have to be stiff, stiff. And therefore, we were able to then discuss how to relax certain constraints with the client very early on in the project. Which brings me to my conclusion. So at Kent, to design the efficient design of floating offshore wind turbine for us relies on 3 pillars: the use of AI tools, some serious computing power or time, and we still need engineering expertise to select the right deterministic models. Thank you for your attention.
Thank you, Johan, for this quite methodological talk, but very clear, so very helpful. So the next speaker is Gisèle Copin from Greenwich. So she's a wind turbine engineer working for Greenwich. She has a master's degree in mechanical engineering, in modeling and experimentation, and she's mostly working on wind turbine and foundation loads design and on the wind farm design through layout optimizations. And the title of the talk is Wind Farm Layout Optimization, or Powerful Solutions to Increase Floating Wind Competitiveness. So Gisèle, the floor is yours.
Okay, sorry. Okay. Hello everyone, I'm Gisèle, and today I would like to talk to you about our technical solution to increase competitiveness of floating wind thanks to layout optimization. Sorry, j'y arrive pas. Okay. First of all, let me briefly introduce my company. Greenwich is a spin-off of IFPN, providing innovative solution and engineering service to the wind sector. We have 4 areas of expertise that you can see above. And today I will present FOWT, our wind farm design solution, available as a service or as a SaaS. Layout optimization is a critical but complex stage of wind farm design. To give some context, we call layout optimization the way we optimize the wind turbine location to minimize wake losses and wind farm costs. There are many challenges in performing this type of numerical optimization. Firstly, it's a multidisciplinary topic, because it combines different technical and economical domains. For example, depending on your objective, you may want to optimize the wind turbine location to increase your energy production or more to reduce your farm costs. So it's also the combination of many constraints, complex zoning, minimum turbine interspacing, even alignment constraints, which are imposed by social acceptance and maritime laws. And to this common constraint, floating wind adds new challenges like mooring constraint, IAC, and these additional challenges complexify optimization because we have to simultaneously search for the best turbine location and for the best mooring and electrical cable orientation. So these challenges make layout optimization complex and time-consuming, and that is why we created a numerical solution. But these bring new scientific challenges, such as complex optimization problem, because we have a lot of parameters and a lot of local extrema, long calculation time, and also we need a need of accurate wake models to compute correctly the energy production. So let's see how we design this numerical solution. To meet all these challenges. So first, we have integrated wind farm inputs, environmental conditions, and we add some project economics models. We also integrated some other project constraints. And next, according to all these parameters and input layout, we can calculate the AEP or some economic indicators. So this is the direct calculation, and usually engineers manually define a first layout, and then they iterate on this layout to get a good AEP. In our case, we use IFPN algorithm developed to optimize layout efficiently. This algorithm takes into account a lot of constraints and work even without an initial layout because there is an initial layout generation integrated into the optimization process. And the optimization stops after reaching a certain level of solution convergence. So that's what it looks like in OptiWits. As mentioned before, to optimize wind farm layout, we need an accurate estimation of the AEP of the farm. This means it's essential to have powerful wake models to accurately estimate the wind deficit induced by upstream wind turbine to a downstream wind turbine. And we use two types of wake models depending on the stage of the project. For example, for first project stages, we will evaluate a lot of different scenarios. In this case, simple wake models are adapted because with them we can optimize in few seconds and get first a good layout quickly. On the other hand, for more advanced project phases, we will be interested in finding the best layout. In this case, we use more advanced wake model developed by IFPN, and these models are a bit slower, but still allow optimization to provide results in few hours. So that's enough for us. I have talked a lot about the optimization constraint, and I would like to be more specific about the floating case. First, what is fully integrated in OptiWits for now is the complex zoning, the minimum turbine interspacing, and the alignment constraint. The two last constraints that I talk about could be combined to model mooring constraint. For example, you can set the minimum interspacing to the mooring radius. But then to be more specific for mooring line orientation, IFPN is developing a special algorithm that is still under development for now. And they are also working on some integration of specific power curves and specific wake models for the floating wind to improve AEP calculation. So what you can see on this picture is the difference in wind deficit that you can have due to the floating movement of the wind turbine. To test our solution and parameterize the optimization, we create different use cases. And I took an example, these use cases, which is a 77 wind turbines of 10 megawatt. The minimum interspacing is of 3 rotor diameters, and the boundary and the wind roses are inspired from Borseleux wind farm. We optimize this case with both alignment or non-alignment constraint. And from this use case, we perform several optimizations. First, we manually generated an aligned layout following the main wind direction. It's the common practice today to create a line layout. And then we did a quick first align optimization using a simple wake models. So in less than a minute, I got an optimized layout with plus 2.1% of AEP gain. So you can see that it's way more efficient than manually generation. Sorry. Yes, and then to test the algorithm with a complex wake model and still with alignment constraint, I ran a third optimization. You can see that in this optimization, we earn even more AEP gain, even if it's more time consuming. But it still took a reasonable time. And finally, I ran a last optimization without alignment constraint, but still with advanced wake models. Because the case is less constrained, we earn even more AEP gain, 4.4%, and the optimization is also faster. So to conclude, I've added a short video of how the optimization is tracked in FOWT. And to summarize, layout optimization has a strong impact on project economics, mainly because of AEP, of the gain of AEP it induces. And it's now possible to save engineering time thanks to performing numerical optimization during wind farm design process. And the next features to be integrated are more specific to floating wind and are currently under development at IFPN. So thank you for listening, and if you have a question, I will take it next. Thank you.
So thank you, Giselle. I feel it is really inspiring to see how you managed to build on research results from IFPN and manage to provide to the industry an operational tool, and I think this is very nice. So the next talk is from Hans Bernhoff, who is a professor at Uppsala University in the Department of Electrical Engineering. So Hans holds a PhD from the Royal Institute of Technology in Sweden in the field of material physics and surface sciences. And he has extensive experience in vertical axis turbines and contributed to the development of several disruptive concepts. And he will be talking on the design tool development for floating offshore wind turbine optimization with numerical and AI tool. Thank you, Hans.
Thank you, Jean-François, for this very nice introduction. And thank you for organizing this excellent conference and also all the talks I've heard here today. I learned a lot, and especially during this last session. So it's a joy to be here and presenting. I'm somewhat of an odd bird here because I'm trying to develop a rather disruptive technology. And I'm doing it partly at Uppsala University and partly at CTO of Worldwide Wind, which is a Norwegian company based in Oslo. And a lot of the work I present here is due to students, PhD students, colleagues, and also all the colleagues at Worldwide Wind, and some of our partners that we work with. So I have not passed you with the whole list. When we do this, we try to do first principle physics. So essentially, we start from basic engineering physics, and we try to do all the models. First, you need a background study. You need to have an analytical basis. You develop simulation tools in different disciplines, as we have heard today, all the way from aerodynamic, structural mechanics, which is a very well-developed field, so we hardly need any new physics there. into energy converter generator modeling, because we adapt the generator to the turbines, mooring models, and hydrodynamic models. We do experiments generally not in a lab tank, rather a small-scale experiment in nature, because then we hit the tough problem. As we used to say, we hit our head in the wall to make sure that we were working with the right problem. And then finally, we try in a spin-off company outside the university to do full-scale demos. And then I got this cooperation with Worldwide Wind in Oslo. So the concept here, we need to go into detail to give you some backgrounds on it. It's 2 counter-rotating turbines sitting on the same axis. So the upper turbine drives the shaft, which goes internally in the mast, and the lower turbine is mounted directly on the mast. The turbines are, as opposed to vertical turbines, which commonly are H turbines, it's a V turbine, so it's designed to tilt, similar to a sailing yacht. It tilts with the wind. It has very simple design, very few parts, essentially 2 moving parts, where one is, of course, is the upper turbine together with the shaft driving the field winding or the rotor of the generator. The other is the lower turbine driving the mast and the float and the armature winding or the stator of the generator. And we take out the power in this counter revolution. That also allows us to cancel out most of the torque, because the reaction torque is taken up between the 2 turbines by the generator. We fully control the turbines by the generator. This is something I demonstrated back in 2010 for a 200 kilowatt vertical axis system. And this demands a special generator. You couldn't do that in a horizontal axis wind turbine because you have optimized the generator for weight and volume. Whereas here we have the generator down in the float, so weight and volume is not really a concern. It's scalable to much larger sizes. That's one inherited from the vertical axis wind turbines. You can easily scale them up to huge sizes. So I've done designs which are over 40 megawatts. And we get reduced wake effects. This is a bit more technical, but basically both turbines produces a lift, which means that they're pushing down the air. So we mix and dissipate the wake faster, which will be interesting to put in the park models, farm models. Currently, we are starting the engineering works on a small demonstrator at 2 megawatts. So it will, 2.4 megawatts, it will be roughly 80 meters high, and there are some other parameters there. The commercial scale, the first commercial scale we're aiming for, which is by the end of this decennium, is in the range of 24 megawatt. And it would stretch almost around 250 meters above the water level and 85 meters below. To do all this, we need a model, since we're doing new technology that no one has done before. So we need to have a model to interact with to see where we can develop the technology in the direction of the sweet spot. And of course, you need to have a mechanical model, an aerodynamic model, a hydrodynamic model, an electromagnetic model to design generators specifically for the turbines and for the conditions. And finally, you need a circuit model to be able to model the control of the turbine and the operations of it. These models has to be integrated. Traditionally, you would integrate there's one arrow too much there. You'd integrate the mechanical and the aerodynamic model into an aeroelastic model. And finally, you add the hydrodynamic model to get an aerohydroelastic model. The electrical models you integrate into an electrodynamic model, and then you need to marry these to be able to model the full VEC. And this has to be done, and finally, of course, you have to do what Giselle told us about. You have to be able to model a park, because it has a huge effect. That's where you want to use the technology. Developing this, we aim to use a user-friendly interface developed in MATLAB, where there's a lot of functions already integrated. we have to have design parameters. I think Johan mentioned 20 to 30 parameters. With this turbine, we are in the range of around 40 parameters, so it gets quite complex. And we need to be able to store this and handle this like any computer-aided design system. We need the models, of course, to do some preliminary analysis. This has to be low fidelity, unless you have a supercomputer, which you generally don't have as a designer. But, and finally, you need to have output to understand both the data and the design itself, 2D and 3D, and a lot of parameters. Yes. Once you've done the design with low model, you can model it with high fidelity models to study different parts, for example, the aerodynamics. We'd like to enable AI integration. I think Johan outlined exactly what we want to do. I'm grateful for that. You have a job if you're interested in coming to Oslo. We need to do a cost optimization because why are we doing this? The goal is to reduce the levelized cost of energy. And as we see today, from today's technology, we need to reduce it by a factor 2 or 3 to make floating wind competitive with land-based wind. And we think this is possible, but in order to do this, we need to find a sweet spot, and then we need to have a cost model for the technology from the start. So we're integrating a cost model based on material use. Finally, of course, we need to validate all the model, otherwise they're useless. So the idea is to validate the low fidelity model with the experiments, but above all with high fidelity models. And the high fidelity models have been, will be, of course, validated by the demonstrators. Future development of this technology would be to replace the semi-empiric low fidelity models with the trained neural networks, exactly like Johan outlined, and to allow a very fast design process. And I would think this is similar to the development we have seen in metrology, where they now, with the neural network, can produce better long-range forecasts than they could with the old supercomputers running more physically based models. And thanks for the attention, and I'm happy to take questions whenever.
Okay, thank you all for the talks. I think we did a pretty good job on the timing, so we have time for questions. We will try to end at 10 past 5. Do you have any question in the room for the speakers? Don't be shy. So I do have one for Hans. So you mentioned that you are working on a design of a prototype. Or do you schedule a deployment at some point? What's the timeline?
Yes, thank you very much. Does this work?
Yeah.
Okay. Yeah, the deployment is aimed at, it's 25 now, 27, so in 2 years. But that's basically depends on seeking the funding this spring, which unfortunately has turned out a little bit harder than we had planned due to international events.
Sure, okay. Thanks. Any other question from the room? Could be anything. So I do maybe have one more for Alexi, and then I'll let you think of one on your side in the room. So you mentioned the fact that maybe X-band radar are the tools that we should use. This is what is existing, and that could provide information to get information on the incoming wave field and in the short term. What would be the best solution to analyze these data that are not directly wave elevation, but radar backscatter to go backscatter to wave elevation?
Okay, well, thank you for the question. It's exactly the topic that we are now working on. So I think the main issue is the lack of ground truth data. So you need to have radar data, and then you have to have wave data in concurrent locations. So this can be achieved by deploying a wave buoy. That's a possibility, but that's quite limited because it's only 1 point, and then what happens in different areas of the radar's field of view can be different. So we are aiming at different solutions that we have not yet implemented at sea, but we should be doing that in the next couple of weeks, hopefully for the first time. So we will send a drone on top of the sea surface to measure the waves directly in bespoke locations in the radar's field of view. And the drone will have a LiDAR that will take direct measurements of the wave field. So that's probably more flexible than a wave buoy.
Okay, yeah, thanks. Looks like a very exciting experiment that we'll conduct. Any question from the room? Otherwise, I'll continue satisfying my curiosity. Okay, so I have one last for Miren. So I know that you are working next to BMEP in Spain. Do you plan to work with the Ash Lab facility to test your algorithm, trying to learn the mooring tension from this lab, from this buoy? Sorry.
Yeah, thank you for the question. At Tecnalia, we have a HAS lab, which is a floating laboratory installed on OpenSea on BMEP. And the idea is that over there we have a lot of sensors and also a spotter buoy in order to measure the wave elevation, everything, and also wind. And the idea is that with this data from the meteorological conditions and with all the sensors that we have put in on the mooring system, on the dynamic cable, and also we put some sensors on the whole of the HAS lab in order to obtain indirect measurements of the tension in order to determine the tension at the mooring system. The idea is that with all of this data, we are working on developing digital twins and different algorithms. So yes, this is the idea, to have a digital HAS lab.
Okay, thanks. I believe that having data at sea, even if it's not on a full-scale unit, it's very valuable. We can learn a lot from that. So.
Yes, not only the data, also to learn how to where to put the sensor, how to put the sensor, because it's not only the data. In order to obtain this data, we need a lot of work. Looking for the best sensor, for the best place, how to install, and because we have problems with a lot of sensors, we put the sensor, and after 1 month, we lost the sensor because the wave came, and it's not so easy to obtain data. So thank you.
Okay, thank you. And thank you all for this session. I think it is time to close this technical session. I hope you have enjoyed the session. And I think they have proven that we have skilled researchers and engineers that are devoted to floating offshore wind sector. And these are a critical link in the chain that must support the deployment of floating offshore wind. And I think we have to be careful not to break that link because we won't succeed in deploying the sector at full scale just with business developers and bankers. And I hope you get the message and support the research that have been shown today. And now I would like to welcome Fanny Moutin on stage from Pôle Mer Méditerranée. She is behind the organization of the event. She is the one responsible for having this very smooth event. You do not notice her work because everything is going so smooth, but it's because she's working so hard. And I would like to welcome her on stage very warmly.
Thank you very much, Jean-François, and thank you to our panelists from these 2 days of conferences. I won't take up much of your evening this evening, so don't worry, I'll be very brief in my closing remarks. I'm very proud that we've managed to make FOWT such a driving force in the industry, and it's really thanks to you all coming back year after year to support us. I would also like to thank Jean-François, our panelists, Louise, who is still in the room, all of the staff from the Quartz in the backstage who are working also to feed you every lunch. I'd like to thank our colleagues from Pôle Mer Méditerranée and from France Renouvelable. I think we can give them a hand and applause. I'm very proud that we were able to have such quality exhibitors and sponsors. Thank you again to Penavel and Ocean Winds for sponsoring us this year.
Thank you to the Région Bretagne for hosting us for the second time. First time in Brest. I have to say we were a bit apprehensive about the weather, but I think we were very lucky in the end this year. And hopefully we'll be just as lucky next year, where we will be going back down to more southern latitudes along the Mediterranean coast. We will be quite close to the AO6 extensions in France, as well as the future AO10 2-gigawatt projects off the coast of France. So we're very pleased to invite you next year to Montpellier, March 24th through 26th. We really hope to see you there, and I wish you a good evening, a good trip home for those who are leaving tonight, and a great visit tomorrow for those who are attending. Thank you all very much once again, and see you next year.